who are joining us a bit late, they can just, watch the recorded session earlier a bit later on. So just in continuation of what I did last week. So I remember I went up through gravimetric. So we have acid-base titration, and we have redox titration. We have rate of reaction. And what else do we have? So I talk about acid-base and redox titration, very popular rates such as that disappearing cross, but there's also the iodine clock reactions where you monitor the time taken for the blue-black color to disappear or for the blue-black color to appear. Not titration, but just rate of reaction experiment. Gravimetric is very popular. So gravimetric came out in the last practical, the one that students in the, I think it was 10 days ago or a week ago, something like that. So most of you are doing the next round of practicals. So, there's no guarantee whether it will come out again or it will not. There is only that idea that everything is as stated in the syllabus. So, you're supposed to have done at least 1 or 2 before. I talked about the collection of masses last week in terms of the labeling as well as the header and stuff. And these 2 are the one that I haven't really talked about last week because we ran out of time in that 1 hour. So I'll just very quickly go through thermometric as well as gas volume experiments. Anytime you got questions, just feel free to stop me and, just let me know. Just shout out if there's anything you wish for me to stop and just discuss a bit further. So just shout out, yeah? So no need to feel embarrassed to interrupt me or anything. So thermometric titrations, well, they can come in various methods. They can come as thermometric titration. They can come as metal displacement, a more reactive metal displacing a less reactive metal. They can also come up as neutralization reactions. They can come up as a carbonate plus acid kind of reaction. They can come out as anything as long as they involve reading a thermometer. That is the most important idea. Gas volume experiments have been very, very popular since 2016 onwards. Can I just ask a quick survey of people here? Isa, if you are there, Isa, have you done anything involving collecting gases yet?
No.
You have never done it before. Okay, Rahiman, have you ever done gas collection experiment where you invert a measuring cylinder? You never? Okay, how about you, Yasmin? Have you ever done this kind of experiment before?
Yes.
Okay, and last but not least, I have Shakira. Shakira, have you done this kind of experiment before?
Yeah, but I was absent on that day.
So you never done it there, okay. Can I ask you to practice doing this, okay? So what you need really is, you need to fill a container with water. Just fill it with tap water. Okay, what you do next is you grab like a bottle. So I'm not sure you can see me on camera, yeah? So what happened there is you want to have a bottle, which is essentially your measuring cylinder, fill it up to the very top. So your bottle will have a slightly narrow opening on top there. So you want it to be like measuring cylinder where it's totally flat one. So it's got a big hole on top, yeah? Okay? So fill it up to the very top. Fill it up to the very top with water. What you want to do is you want to hold it with your hand, with the palm of your hand, hold it tight, hold it tight. The instruction is always saying use paper, but then people get scared if you've never done this before, okay? Is this thing, okay? I don't teach A-level, so I don't know whether it's going to come out or not, but it is in the syllabus. It's quite popular since 2016 when it was first introduced, and even is in all-level syllabus nowadays. So you want to hold it with your hand. So pretend this is open now, okay? So I'm just going to close it. So your measuring cylinder don't have a closing, so you just have to hold it with your hand. Make sure it's full, and then you have that water trout. This is called water trout, or they call it water basin. So it's just a huge basin filled with water. Your job is to invert this fully filled measuring cylinder, hold it tight with the palm of your hand, invert it very quickly, immerse it into the water trout. Because if you let go of your hand before you dip it into the water trout, the water is gonna leak. And when the water leaks, you will have this thing on top where your measuring cylinder is not starting from 0. You want your measuring cylinder to start from 0, then whatever gas is being produced will push the water level down, and then you can read the reading. When you read the reading, you don't read it upward, you read it downwards. Because if you are a very good chemist and you didn't lose anything, you will have started from 0 at the very top there, so that your measuring cylinder is going to look like this. So I know it's easier said than done, and you're not allowed to go into the lab now that lab will be closed in preparation for your exam. So it's essentially looking like this, where you will have your conical flask, and then this is your side arm, and then that is your rubber bunk. This is your rubber bunk to prevent the gas from escaping, and this is your reaction mixture, and they will produce the gas, and they will displace water. So this is a measuring cylinder. A measuring cylinder is not the most accurate thing to measure volume, but they can measure volume regardless. Instead of using a gas syringe, in fact, they usually prefer in practical chemistry, in practical paper 3, they usually prefer using a measuring cylinder because number one, it is bound to work. Okay, if you use a gas syringe, sometimes gas syringe has that rubber inlet, which if you don't produce a large amount of gas, it doesn't push out the gas syringe that much. And in a practical, this is the one that is bound to work rather than a gas syringe. On paper, gas syringe is better than this particular method because some gases can dissolve in water. If some gases dissolve in water, then you're not going to collect accurate volume. And of course, if you already collected the gas and stuff, and there might be some air left in there, which might fill up the space in there as well. So not all the gas collected might be the gas that you want. Okay, so I'm just saying that there are a couple of reactions that produce gases, one of which here is as stated, carbon dioxide. You will know this from reaction of acid in O level. Metal plus acid give you metal salt. This metal salt produces hydrogen gas as well. So this is a key step to produce hydrogen gas. Oops, where was I? Hang on, just give me a minute. I don't know what was wrong. Sorry, where's my metal carbonate? Yep, the other reaction will be metal carbonate. So when you have metal carbonate plus acid, so in practical, it's mostly about your practical skill rather than about your theory, but of course there'll be calculation associated with it as well. So I better show you a couple of questions. Like for example, in gas volume collections, there is one. So I've got a couple here. This is a June 2016. So from 2016 onwards, gas collection came out. Okay, it was in the syllabus from 2016 onwards. So it's not new in 2022. It has been in the syllabus since March 2016. That was the first time March March paper actually appeared. So here you determine the AR by collecting gas. So you can do it this way or this way, the left side or the right side. I've seen most school laboratories in Brunei. It's very rare that we have this sidearm because it's a specialized apparatus. So what we have really is this particular kind of thing where we have a normal conical flask and we have this delivery tube. It's just a rubber delivery tube really, rather than a glass. So like I said, you invert your measuring cylinder, don't let go, hold it tight with the palm of your hands. You see the instruction, they say fill it up completely with water and then hold a piece of paper towel firmly over the top. So if you are doing this for the first time in the exam, it might seem a bit scary. And the more you do it, the more you spill the water, the more you get nervous and you won't be able to complete the exam later on. It's not worth a lot of marks. It's 2 marks and then 3 marks or 5 marks altogether. But it is the first question, and it will disturb the momentum as you are doing the exam. And momentum is everything because it affects the mood for the rest of your exam. So you want to be able to do this. So at least practice it with a water bottle. Okay. So your goal is to. I know your water bottle don't have measurements on it, unlike measuring cylinder. Your goal is to lose nothing. You don't want there to be any gap at all. You want to have it completely filled so that you'll be able to start to read from 0 cm cube then. Okay, this was what I told you last time. So I hope you have done something about it. And if this comes up for the next practical, or if it comes up for your November practical, you've got to be at least able to do this. I think doing the actual practical and collecting the volume should be easy enough. And then you need to clamp it because nothing can hold your measuring cylinder. You don't want it to, lie flat on there because otherwise you cannot collect the volume of gas. So you hold it on a red top stand and then it will be it's still immersed, but it's just above the level. Make sure your delivery tube is inserted underneath because some people, they lose the gas. They didn't take note of the delivery tube. the tube is actually hanging outside. Then there are no gas being formed. Of course, because if your delivery tube is outside, the gas is going to join air. Whereas when it's here, the gas will be collected here instead of joining the air molecules outside there. So make sure you have everything set up. You open the thing there, put in your acid or put in your solid, and then close the bung very quickly, and you will see bubbles. So you will know the reaction is complete when there are no more bubbles, because no more bubbles mean no more gases. No more gases means, well, reaction is complete because nothing else gets produced. And then you will read starting from 0 cm cube. We don't read 1 decimal place because measuring cylinder is not burette, it's not the most accurate thing in the world. So you started reading and then you read the final volume. Then how about sometimes you say, I am not a very good chemist, then sometimes you started from like this. You could have started from 10 cm cube or 5 cm cube, and that would be your initial reading. And then you will have final minus initial. That could work as well if you are really desperate, but you should at least make the effort to try and get nothing lost at all. That's the reason why they want you to fill it completely with water in the first place. The instruction is really long, but the idea is just results. So you're supposed to collect a couple of results, and for 2 marks, what are you supposed to do here? You need to use pipette, this much acid. So the fact that you use pipette means that this is quite an accurate volume. This is quite accurate volume, just like when you're using burette. And then the biggest error would have come from gas loss. So your job is to minimize the gas loss in this kind of experiment. What else can I tell you? Weigh the magnesium ribbons and record the mass. So when you weigh the magnesium ribbons, you need to record the mass, so you have mass of magnesium, and then make sure that you have header as well as unit as well, and then you have the value, and then this will be swirling the flask occasionally. So you need to swirl, just like when you do titrations, until no more gas is formed. That means the reaction is complete, and then you will record the volume of gas. Volume of gas is a 3-dimensional unit, so it's cm cube as measured on the measuring cylinder. You use measuring cylinder to measure volume of liquid usually, but here you're using the measuring cylinder to measure the volume of gas, and this is in cm cube. So be very careful. This is about magnesium reacting with H2SO4. So you have the volume of H2, and you are reacting all the magnesium, I think. Am I reacting all the magnesium? Yeah, because the acid is in excess. If the acid is in excess, that means all the magnesium reacted. There are 2 ways you can tell this reaction is complete: when there are no more bubbles, and also when there are no more magnesium, because all the magnesium would have reacted. So we are going to relate the mole of magnesium, which is 1 mole, is to the mole of hydrogen gas, which is 1 mole. You have the volume of hydrogen, and this is in cm cube. So you would divide by 24,000 cm cube per mole. This is the 24 dn cube per mole as given in a periodic table. In the new paper 3, starting from 2016 onwards, periodic table is as given in the paper 3 itself. And then you have the mass of magnesium, you have the relative atomic mass of magnesium. Altogether, this is what you want, this is what you have, what you have, what you have. Unit manipulation is very important. Find the AR of magnesium. Now, we were told that the periodic table is given in the exam itself, and you know the relative atomic mass of magnesium is something sensible. I think it's 24.1 in the periodic table. Then if you get something which is, I don't know, 24,000 or 0.024, you know you have gotten the mistake of either forgetting to convert this to dn cube, or you have forgotten to use 24,000 when you get a ridiculous number. So, just something for you to keep an eye out of. 6.2, this is very similar. Now, this is a different story. This is winter 2016. So November 2016, paper 3-4. Okay, you cannot just think about paper 3-5 or 3-4. I don't know whichever one you're doing next week, because any of the practicals, they are just different variants that could be applied to different contexts. The teachers in the school have no jurisdiction over what can come out, because it's all based on Cambridge discretion, and it's all as stated in the syllabus. This is collection of gas. How in the world do you do this? It's the same method. Okay, so you will fill the tub with water. So this is your water tub, water trough, water basin, and then you will fill the burette. So you fill the burette, but this one is, what do they want? to add about 20 cm cube, add distilled water to reach 0 cm cube. So here you don't fill up the burette to the very top. This is even trickier compared to the last one because there's instruction there. I leave you to read this on your own, but it's still gas collection, winter 2016, paper 3-4, question number 1. Burette is going to be more accurate than the measuring cylinder for reading volume of gas because they can record up to 0.05 cm cube for a single reading. So this is just a little bit of ideas which I went through in my other tutorials. So when you have one single reading, you have initial reading. So when you have initial reading, I don't know, 0.15, let's say cm cube, if this is your initial volume. So this is already plus minus 0.05 cm cube. And then you have your final volume, which is, I don't know, give or take maybe 10.20 cm cube. So this is not titration, this is collective volume of gas. So this minus this will give you a reading from the burette for your volume. So therefore we have to multiply by 2 because this is for one single reading, but you have 2 readings to involve for one burette reading. Final volume minus initial volume. That's why we multiply by 2 before we divide by the titer. Same thing with the masses. Remember when you weigh the mass of the magnesium, magnesium ribbon, you could measure it on top of the mass balance. Then you say, but I'm doing one reading only. I'm just putting straight away the magnesium ribbon on top of the mass balance, right? There's just one reading. But what did you do before you do that? You will press the 0 or the T button, that is the tare button. Usually when we measure powder, we don't put the powder on top of the mass balance. We will have like a container or a small bottle or a crucible or whatever. Then we press the 0 or the T button, then we weigh the powder. But if this is magnesium ribbon, we could have just put the magnesium ribbon on top of the mass balance. Then some students say, why do I still need to multiply by 2? Because you did press the T buttons. If you didn't press the T button, you wouldn't know to start from 0. When you press the T or the 0 button, you are saying read the initial volume, read the initial mass as 0.00 gram. So that is what you're doing. Take away whatever initial mass it was. There was whatever the mass of A or whatever, which is very light, but take away that mass. So essentially, you're going to do final minus initial. It's just your initial was 0.00 based on the mass balance reading. So don't forget, mass reading is always multiplied by 2 for the error in a single reading, multiplied by 2 because you always have final minus initial mass there. I think the rest of the questions are pretty much similar. You see 3 marks to collect the whatever thing because burette, you really need to read twice rather than measuring cylinder, which was just reading once. And the question itself is not too bad. This is higher amount of marks. This is talking about temperature and volume of gas. So temperature affect rate of reactions. How fast is rate? But you are collecting volume of gas. That is how much. How much is amount? How much you actually get. So be very careful, yeah. This one is about the percentage error in mass and volume. I already mentioned that. If you want to reduce the percentage error in mass, so if you have the percentage error in mass, error in a single reading, forget about the plus minus, it's just something for me to remind myself. As you know, you have 0.00, 0.01, 0.02, these are gram. So the smallest division is 0.01 gram. So therefore the error is the smallest division divided by 2. So that's 0.005 gram. This is for a single reading. That is what you would have done as upper bound and lower bound in lower secondary mathematics. I think from 1 math or from 2 math, you will have learned about upper bound and lower bound. So this is multiplied by 2 divided by the mass of recorder times 100%. If you want to decrease the error, you want the error to be smaller. This question can also be changed to improve accuracy. If you want to improve accuracy, you want it to be more accurate. Therefore, you want the error to be smaller. So when you want the error to be smaller, your experiment is more accurate. Vice versa, if you want to improve accuracy, you want the error to be smaller. So think back on your percentage error and the formula. If you want this to be smaller, error to be smaller, the mass needs to be bigger. So you can use a bigger mass than what you have. But then you don't want to use infinite mass, because if you use infinite amount of mass, yes, error is very low, But one, you're wasting chemical, and two, you're waiting for a long time for the reaction to finish, because you need to finish the reaction and then you collect the gas, and your burette might not be enough when you use a very, very large amount of your starting material. So something practical to be used in the lab. But what you don't want is, you don't want a mass of 0.01 gram. That is going to be very small mass and give you very big error in the mass, and therefore very inaccurate kind of experimental result. That is mass. You could be thinking about percentage in the burette reading, which of course, it reads your title volume. So it's the volume of your title, final minus initial. So it's 2 reading, and each burette reading is 0.05 cm³ difference. So again, when you do titration, you don't want your titration volume to be, I don't know, 1 cm³. If you pass 1 cm³ and then your titration is finished, it's not going to be a very good titration, because when your volume of title is very small, something divided by very small will be very big in your error. That means your titration won't be so accurate. Your burette can measure up to 50 cm³, but neither do I want 50 cm³ bottle to be my title, because it will be a waste of chemical, and it will take a much longer time for me to do the titration, as I will need a greater amount of volume from the burette, and I would need a greater amount of volume of the stuff that I prepared out. So it's a waste of chemical again. So I want it to be something sensible. Most of the time, your titration is usually, I don't know, 20, 30 cm³, something like that. Yeah. So hopefully that makes sense to you. Just to introduce to you a couple of other reactions that produce gas. We talk about formation of carbon dioxide, formation of hydrogen gas. This is another key reaction. This one is not acid reaction, it's just hydrogen peroxide decomposing to give you oxygen. You might have learned this where you use MnO2, manganese 4 oxide, as catalyst. It's one of the most popular questions in O-level and IGCSE level chemistry. So it's a black solid. In fact, they can ask you this in qualitative analysis. Because when they give you in qualitative analysis, they can ask you to test this colorless liquid. So they say, to this liquid or whatever solution in a small test tube, add this solid, and then observe what happened. Well, if you add a little bit of MnO2 to H2O2, what will happen is you will see effervescence. Now, you are adding a black solid to a colorless solution. Black solid, this is a black solid to a colorless solution, and you get an effervescence. It is less likely. I'm not saying that it cannot be carbonate. I'm saying that it is less likely it will be carbon dioxide. And in addition to carbon dioxide, because carbon dioxide will, you test it with lime water. Before you test with lime water, you should always test for lighter splint or glowing splint. But you could test for hydrogen or oxygen. Then is there a pop sound? Then there will be hydrogen. Does it relight glowing splint? Which in this case it will, because it produces oxygen gas. One of the ways to produce oxygen gas easily in the lab is to add a black solid and an catalyst to speed up this decomposition. This effervescence, it really, really is quite easy to see. It relights the glowing splint quite easily. I hope you have seen this experiment before. And if you haven't, just mention it in the Google Classroom and I'll send you a video on it. You can also watch online as well, I guess. And then, yeah, it's the same setup. That's all I can tell you. So this was March 2017, so quite popular, yeah. So last one is the one specified in their syllabus, 2016. This is about calcium carbonate. So this is just the formation of carbon dioxide. Again, the exact same setup, But carbon dioxide, you know something about carbonated drink? You see this one? I think not all the carbon dioxide given up is collected in the measuring cylinder. You think about carbonated drink. So carbon dioxide can dissolve in water because we can get carbonated drink. So, so if we collect it over water, your carbon dioxide is passing through some water. Yes, it needs to be under high pressure for you to, insert carbon dioxide into water, like to dissolve a large amount of carbon dioxide in water. But regardless, some of your carbon dioxide would actually dissolve in the water content within the water tub or the water trout. So you won't be collecting the exact volume of carbon dioxide here. So if you want to collect carbon dioxide, this method might not give you 100% accurate volume, but they will be very close to the accurate volume of the carbon dioxide produced. But if they say you want to improve, you want to get the increase in the volume of carbon dioxide collected, change in the method. So this kind of question, yeah, you need to read very carefully. Method. So some students, they will say use lesser reactant, use more reactant, but reactant is the reacting amount. Method is the procedure. Procedure, methodology, it's got nothing to do with use more reactant or whatever. So I guess this is just changing it to use a gas syringe. If you use a gas syringe is not typically what they'll ask you to do in your actual practical, as I said, because it's not actually that easy to collect volume of gas with a gas syringe compared to using this inverted measuring cylinder method. Okay, so that's it really on measuring volume of gas. I mean, this was just something that my students did before. You could have done initial volume of gas, but by right, it should be 0 because if you're competent enough, they should start off from 0. And this is something you have to practice on your own for the fear that, you know, the actual thing might come out and then you might not be able to do it. Now, these are just a list of thermometric titration. I'm just going to go through a couple as I have outlined them to, well, I kind of like condensed them down to a few that are very, very popular. So just one of my former students kind of work. Hope you have actually done this before, but knowing how COVID actually happened last year and this year we had that long period of shutdown. So you just have to, you know, be able to do these kind of things. Otherwise, you won't be able to score, okay? Now, this is instruction. This was already pre-weighed in a bottle. So there are 2 weighing bottles because you do them twice, okay? You do them twice. Now, you will see that the mass of the solid content within the bottle, they are between this range because that was what the supervisor would have been instructed to weigh out for you, or the lab tech would have been instructed to weigh out for you. So they wouldn't be, you know, they wouldn't be above that. If they are above that, you need to rest out with your supervisor or something. But of course, follow instructions. You can have 2.91, 2.92, 2.93, but by right, it shouldn't be that different from there. I think on the day that I was supposed to weigh for the students, I think I must have used just slightly above 3 there. Anyway, it doesn't matter. So when you label your header, make sure you have header for masses. What are you recording? Do you have the mass of the empty bottle? So this is just the mass of the empty bottle, essentially. So the students say without the solid. So that means it's just the mass of the empty bottle. And don't forget your units. Rather than writing down units all over the place, you should know already how to label your header, as you would know from paper 5 experimental planning or paper 4 alternative to practical from O-level chemistry. So this is just, you know, the difference that tell you the mass of the solid used. The reason you do them twice is because, you know, when you repeat experiments, you improve the reliability. You can see whether you made a mistake in one of the reading when the 2 results are extremely different. This kind of calorimetry experiments is very, very common. You have a plastic cup, essentially a styrofoam cup, supported on a beaker. When you wash or when you rinse the styrofoam cup, please do not rinse the beaker. Just take out the styrofoam cup and pour it out and rinse it. When you rinse, because you need to repeat the experiment, when you rinse or when you wash the cup, make sure you wash the thermometer as well. Some students, they forget that thermometer measures temperature, and your reaction from the previous reaction essentially might be endothermic, might be exothermic. And if you don't wash the thermometer, it might have impurities. It might still read the temperature from the last experiment. So it's important that we rinse the thermometer with some distilled water as well before we repeat the experiment. Blah, blah, blah. So you put in the solutions and then you put in the solid. This is a reaction between zinc solid and copper 2+ ions. So this is a metal displacement. As I mentioned there, redox. As you know about the most reactive metal to the least reactive metal, these are your polycarmazole, blah, 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 and then zinc, and then hydrogen, and then copper. So you have zinc, which is a more reactive metal than copper. So zinc will displace Cu2+. Of course, how can this question change? I can also give you magnesium and copper 2 sulfate. I can give you magnesium and zinc sulfate, and the reaction will happen because there is a difference in the reactivity, and therefore there will be a redox reaction, which is spontaneous and feasible, and it will be exothermic, and that is why my temperature will increase. You're asked to record the temperature every half minute, except when you add in the solid. Except when you add in the solid. Now you understand why this student did not have the same temperature, did not have the same time at which he added the solid. It's because he followed the instruction. Do not read the temperature, blah, blah, blah. Where was it? Until a steady temperature has been obtained for a period of at least 2 minutes. When you immerse the thermometer into the solution, you're supposed to wait for a little bit before you actually start the reaction, because your thermometer needs some time to equilibrate to come to the actual temperature of the solution. Because previously it was in the air, it might be measuring the temperature of your surrounding instead. So once you start the experiment, you don't read it for 1 minute, but you can see the temperature suddenly rises all the way, become very hot. This reaction is going to be exothermic. When you do calorimetry, you can tell straight away. The moment you open the exam question paper, you can tell what kind of experiment it is, okay? So the one that happened, I think paper 3.3, the one last time was titration, acid-base, and gravimetric analysis, and qualitative analysis, so 3 questions. So when you see there's something to do with thermometer, then you know it's calorimetry, MC delta T kind of thing. There could be a graph, so they always ask you, make sure whatever highest temperature you have, your graph should extend 10 degrees Celsius above, because you're going to do extrapolation. This is the kind of result, actual experimental result. Steady temperature at the beginning, so you draw one line across. You draw one line across with your ruler. You draw one line across with your ruler, steady temperature. This is what happened afterwards, because as the time progresses, the solution will cool down after it heated out all the way. So you're supposed to draw these straight lines all the way. So that is the meaning of extrapolation. Extrapolate your data. Extrapolate your data. When do you add? When do you add the solid? This is key. Yeah? This depends on when do you add the solid. When you add the solid, you do not measure the temperature straight away, because we calculate it from the graph. We cannot measure the highest temperature the moment the solid gets in contact with the solution. So instead, we extrapolate the graph, and then we draw this line here to indicate where do they intersect. Where they intersect, such as this is your final temperature. But this was the time on the x-axis. This is the time when you added in the solid, when you kickstart the reaction. So this is the highest temperature reached, but this is final temperature in degrees Celsius. Initial temperature is not 0. Initial temperature is for your solution based on experimental results. So make sure whatever you do, you have final temperature minus initial temperature. Temperature has shot up because the surrounding receives the energy, because the system, the reaction gives out the energy, and the surrounding absorb the energy. Conservation of energy, energy released by the reaction is absorbed by the solution, by the surrounding exothermic reaction. You are averaging these 2 experiments, so you get this average temperature. One of the key concepts in this kind of experiments that a lot of students mistook, and I think I went through this with you in the theory, you have solutions, and then you tip in the solid. So my diagram is not very good, so pardon my diagram. So your solid goes in. Now your solution is assumed to be water. So if you don't assume it to be water, you are going to have a difficult time. So why do we assume it to be water? Because we want the density of water. We know the density of water is 1 gram per cm cube. So whatever volume of water you have, whatever volume of solution is the volume of water. Whatever the volume is in cm cube, that is your mass in gram based on the density of water. We are talking about delta T, which is change in temperature. So we have not delta H, but Q equal to MC delta T. This is heat energy. Q is not enthalpy. Q is energy. The MC delta T is of the water, because heat capacity of the water. Your thermometer was immersed in the water. It measures the temperature change of the water of the solution. So the key mistake here is the M. What is M? M is the mass of the water, because you are raising the temperature of the water. You are not raising the temperature of the solid. Remember, this MC delta T refers to the solution. So the key mistake is you measure the mass of the solid. Now students think mass is mass, so they want to put the mass here. number one mistake. Do not put the mass of solid in here. Do not add in the mass of solid and the mass of the solution, because you are raising the temperature of the solution. The solid does not dissolve in the solution. The solid reacts with the solution, you see? The solid reacts with the solution. So you're raising the temperature of the solution, which remains the same volume, therefore the same mass of the solution. Then where in the world do you put in the mass of the solid? Well, the solid reacts with the solution and you get a reaction. So the solid is actually part of the system. The water, the solution, is part of the surrounding. So this is the system, and therefore the delta H, sorry, the Q is for the surrounding, the delta H is for the system. Because it's for the reactions, it's going to be the opposite, equal and opposite, minus Q from the surrounding, divided by the mole of the reactant. And this thing is in mole. This thing should be in kilojoule. This thing will be minus, because if your delta T is positive, that means your reaction is exothermic. Okay, temperature increases. If Q is positive, then the delta H will be negative times positive, which is negative, because it will be exothermic reaction. Delta H must have sign, value, and unit. Sign, value, and unit. Something for you to think about, yeah? And then one thing is, this thing, the C is given as 4.18 or sometimes 4.3 given in the question. This is 4.3 joule required to raise the temperature of 1 cm³ of any solution. So it's per cm³ per degree Celsius. So when you multiply that by the volume of the solution, volume of the water in cm³, multiplied by the delta T in cm³, you are going to get joule. This is heat energy given up to the surrounding in joule. But then when you see delta H, there is no sign given, but you must remember sign, value, the unit there is kilojoule per mole. So the kilojoule, you have to divide by 1,000. So something for you to think about it. This kind of physical chemistry, it all comes down to bookkeeping. If you want to score in a practical, you have to know how to do it, but you also need to know the workarounds, some of these mathematical issues as well, yeah? So I hope that is all right there. One more thing I can remind you of is change in temperature. Some people say, change in temperature, they have to add 273. But if this is temperature in degrees Celsius, let's say this is 25, let's say this is, 35 degrees Celsius. Now, when I have the temperature in Kelvin, how would this look like? If I style this to make it pink, so I'm looking at plus 273, which is 298, and then this will be 308 Kelvin. We're talking about change in temperature. So 35 minus 25, this is 10 degree, oops, I should use a different color. That is 10 degrees Celsius difference. And then when you look at 298 and 308, if I have added them both like that, that will also be 10 degrees Celsius. So change in temperature is relative. Something minus something, the change in degrees Celsius is the same as the change in Kelvin. That's my point there, okay? So the change in degrees Celsius is the same as the change in Kelvin. So when we get the delta T, it doesn't matter. I don't know why I write cm³ there. Delta T should be in degrees Celsius there, but it's also equal to the delta T in Kelvin. If this is 4.3 joule, I require to raise the temperature of 1 cm³ or 1 gram by 1 degree Celsius or 1 Kelvin. They all mean the exact same thing there. Anyway, so the next thing is all about error analysis. As with any practicals, you must know about the existence of error. This is calorimetry, something to do with heat energy, losing heat energy or absorbing heat energy. This is exothermic, so it's got something to do with heat release. So the biggest source of error is to do with heat loss. When you think about calorimetry experiment, think about heat loss. Then explain where is the heat loss from? You did it in a plastic cup like this, so the heat that you release the solution can also be released to the air as well. So you can cover up with a lid, so that is quite a common thing. Is you put in the solid already, cover with a plastic lid. We use plastic because plastic is an insulator, just like this is a polystyrene or a styrofoam cup. It is a good insulator, and that's why they keep your hot drink hot for longer, right? Rather than a metal cup, which is a good conductor, and then it will emit and cool down much faster. Another thing is you could put some cotton wool inside. So this is not what you did, but this is what you could have done in order to reduce heat loss and stuff, etc., etc. So very common kind of thing. Yeah? Another thing they will ask you will be percentage error in delta T. Delta T was measured as two different readings: final temperature minus initial temperature. Each temperature has a plus minus 0.5 degrees Celsius. I put the plus minus there to indicate that it's plus minus, but when we calculate the percentage error, we don't have to incorporate the plus minus like that, but we need two readings because we have final reading, which is plus minus 0.5, initial reading, which is plus minus 0.5. So to get the delta T, we need two temperature readings. Like I said last week, there are only a couple of things that don't require two readings, such as time. When you do stopwatch, it's one time reading. When you do pipette volume, one time reading. When you do measuring cylinder, most of the time measuring cylinder is one time reading, okay? Unless you are not very competent with your inverted measuring cylinder. Delta T, thermometer, two readings. Masses, two reading. Burette, two readings, okay? So that's it really on that first one. The second experiment is an acid-base titration. So I only have 15 more minutes, so I better speed up a little bit. This is enthalpy change of neutralization. This is a real exam paper from November 2011, paper 3-4, but it is still within the syllabus, okay? So they did say anything that involves temperature change, and this is also a common all-level titration. This is called thermometric titration. So in these titrations, we don't use indicator. We just simply work out the endpoint by looking at where they intersect. All of these temperatures are recorded to 0.5 degrees Celsius, including the difference. Your calculator is not very clever. When you press 32.0 minus 23.0, your calculator will show you 9. The moment when you have one reading that doesn't record to 0.5 degrees Celsius accuracy, you will lose one of the marks automatically. Accuracy marks depends on your practical and how far away they are from your supervisor. Do not try and predict the trend. Instead, do the practical, interpret the result later on. You should know from your theory that this result is supposed to result in an intersection. It's not a continuous straight line graph like this. It's supposed to intersect like this. Where they intersect, that is the endpoint. This is called thermometric titration between an acid and a base. Where they intersect is the endpoint. This is your temperature change because they ask you to plot temperature change on the y-axis and the volume of the FB1 on the x-axis. So FB1, the volume that you read from your reading, and you should know whether it starts from 0 or not, depending on what is on the x-axis. When you want to decide, does it cut through origin or not, what is your x-axis? FB1 is the reactant. FB1 is NaOH. If there is no NaOH, there will be no neutralizations. No neutralizations, how can there be any temperature change? Neutralization is exothermic. Every single neutralization involve H plus OH minus give you H2O. This is only bond formation. If you think about if there's any bond being broken, there is no bond that's being broken at all, because if you draw it out, you can see it. No bond is broken. There's already one covalent bond there, and you're forming another covalent bond. Even all-level student knows this. Neutralization is exothermic. In A2, you will have learned Kw. Kw is water dissociation constant. The opposite dissociation of water is endothermic, because the formation of water from H plus and OH minus, neutralization is exothermic. They result in a positive temperature change because Tf minus Ti is positive like that. And then after the endpoint, after your endpoint, that means you don't release any extra heat energy because you already have enough to neutralize. So whatever extra FB1, whatever extra NaOH you add, is not going to give you more neutralizations. Therefore, no extra heat is released. But this is like adding water to your hot Maggi or your hot soup. That means whatever extra solutions they added, they don't give up more heat energy. They will just cool your solution down. So yes, whatever amount you have will neutralize the existing acid, but the extra volume of NaOH is just there, and it will cool down the solution because they will not get neutralized as they are present in excess. And that is why the temperature will drop afterwards. The rest of the questions is pretty much straightforward because you have delta T and then you have the volume of the NaOH. Now, when you do this kind of questions, the trickiest bit, this is to find the enthalpy of neutralization. The trickiest bit in this question comes down to whether you understand what's going on or not. Your thermometer is like that. What have you mixed? You have mixed acid and you have mixed some base in there. Remember your MC delta T, your Q equal to MC delta T. The Q there is of the solution because the heat capacity of water, the temperature change of the solution, which is water. So M is the mass of the solution, mass of the solution. You cannot just think about what was in the thing originally because you are not adding acid. Sorry, you're not adding solid. You are adding solution to solution. You're adding solution to solution. So look carefully, solution to solution. So altogether, you will see in each experiment, you add up to 50. In each experiment, they add up to 50. So altogether, in each experiment, you add up to 50 cm3. So in each experiment, there is 50 cm3 of solution. So it's not just what you add, but it's also what you have in the cup altogether, the total volume of solution. So if you have 50 cm3, you will have 50 grams like that. So that's the key thing that a lot of students mess up. Okay, so just don't mess up. If you see this particular student, so you won't be the first one to make that mistake. Just make sure it will not happen ever again. Otherwise, you will mess up. This is given in joule, so do not convert to kilojoule because the unit is joule. But they always want you to work out the enthalpy change in terms of kilojoule per mole, and then you must have a sign, a value, and a unit. Enthalpy change and neutralization, if you get positive, you know it's wrong already based on the equation I just showed you, which even year 9 students know, just forming covalent bonds. Year 10, bond formation is exothermic. Year 9, ionic equations, neutralizations from water, so that is exothermic reaction. So there is something called error carried forward. So, I wouldn't be too worried as I'm doing practical if I know my method is correct. But you should ideally always try to ensure that whatever you do is correct in terms of the values. So always think as you go through the practical, there might not be time to go back and check your answer. That's my point. Okay. So convert your joule to kilojoule, which this student did, and therefore you can get the ECF marks. Okay. I don't think there's much more I can talk about. This is one of those things. I did say heat loss is very important, but sometimes questions say other than heat loss. When they say other than heat loss or in addition to heat loss, do not say it again. Repeating question means you don't read the question and therefore you will struggle to get any marks at all. So rather than talking about heat loss, you can talk about the procedure or the apparatus you use, something which is more precise, for instance, can give you more accurate results and therefore lesser error. Blah, blah, blah. I guess this is a 1:2. This was in paper 3.3. I think out of all of you, I did ask you last week. Akila was the one who did the exam last week, right, Akila? Am I correct?
Yes.
And Akila, it was sulfuric acid and NaOH, wasn't it? Was it sulfuric acid? No. Okay, I was wrong then. Maybe I was wrong. But it was acid-base reaction. That was what I found out. Okay, it was acid-base reaction. You must be aware that there are some stuff which is not 1:1. So sulfuric acid has 2H+, so 1H2SO4 reacts with 2 NaOH. This was my student, so my student normally do my method. You can do whatever method you want as long as you get to the correct answer. This is just using the mole fraction, like specifying the fraction there. Okay, this is a qualitative analysis, so this has got nothing to do with this particular thermometric titration. How can you prove it's sulfuric acid for how many marks actually? 1, 2, 3, 4. So this is 2 marks. How do you prove it's sulfuric acid? How can you prove it has H+? How can you prove it has SO4 2-? If you prove that it is acid, you use carbonate. Carbonate reacts with acid. Okay, carbonate reacts with acid and give you carbon dioxide gas, which you need to test for with lime water. Sulfate, well, you add some aqueous barium nitrate. After you add some nitric acid, then aqueous barium nitrate or barium chloride, and you get a white precipitate. They are all stated in your paper 3 qualitative analysis notes after all. Third one, this is a this is a metal and acid reactions. So just now you saw metal and acid give you metal, salt, and hydrogen. It can be a gas collection, but examiners are quite clever, yeah. So sometimes they have one question which is like using the same equipment. So this is exothermic, so they could ask you to do calorimetry, and then in the other question they can ask you to collect the volume of gas. It's just the way questions are rearranged, and questions are, they try to make the question different, but essentially everything is from the syllabus. That's all I can tell you. Okay. You add the solid at 3.5 minutes, so you don't do the reading at 3.5 minutes, and you can see the temperature increases straight afterwards. Metal plus acid is an exothermic reaction. So as usual, make sure your maximum temperature, you leave some space. Usually they say 5, sometimes it's 10 degrees Celsius, because after some time, the temperature will drop. Extrapolate. Extra means you extend. Polate, you extend the lines onto this point here. Why specifically we draw a line at this point? Because this is where you add the solid at 3.5 minutes. Initial temperature, final temperature. Do not read this as delta T. This is a temperature. This is a temperature. Delta T is change in temperature. Graph, make sure you have level and units. Level and units. If you are not starting from 0, I'm sure, does everyone know what this symbol means? Who hasn't seen this before? Who has never seen this before? Anyone? Everyone has seen this before? Okay, so if no one answers, I assume everyone has seen this before. This is what happened. This is what you should do if you don't start from 0. If you start from 0, 0, it's fine. If you don't start from 0, it simply means that I could start from, I don't know, 24.0 and then 25.0. It simply means whatever is in between, I have a break that I don't start from 0. But I don't think they'll penalize you greatly on that. One last thing, do not ever write. You see, this paper is scanned. This is what happened with your actual exam paper. It will be scanned. It will be marked on screen by some examiners somewhere in the UK or somewhere in the world. The problem is this one, if it is scanned in black and white, you see how difficult it is to read inside the thing there. And they're trying to save bandwidth and stuff because data is expensive, yeah? So what happened is, do not ever write inside the table. Do not use a red colored ink or any color ink. Use a dark enough pencil. Use dark color pen like blue or black, and write clearly. If you're writing in pencil, which you do, you know, for plotting graph, make sure it's dark and make sure it's not faint. Some people, they write very, very light, very, very small handwriting. This handwriting is okay. Can you imagine if you write like this? This is A, B, C, D. If this is how it appears on your screen, this is how it appears for the examiner. They don't like you at all. If you do this, they don't like you at all from the beginning. They are not going to be happy marking your paper. So they are not going to be happy with you at all. So be very careful, all right? So yeah, okay. What else can I tell you? I mean, this is magnesium acid. Last but not least, this is another variation. This is endothermic. Endothermic, but this is reaction of sodium carbonate with water. So this is the reactions. This is from 2013. And I think it's come out once, even after 2013 as well. It's quite a popular paper 5 question as well. So make sure you know how to do this kind of thing. You cannot work out delta H directly, but you can use Hess law. Just now in the syllabus, it said, including any application of Hess law. Here, we are going to react this with acid. They will give us salt, water, and carbon dioxide. We are going to react this with acid. They will give us the same product, salt, H2O, and CO2. They give me the same product. So the reaction here is not formation, it's not combustion, it's not neutralization. It is reaction with acid. Reaction with acid coming down. Reaction with acid coming down. Reacting 1 mole. So enthalpy change is kilojoule per mole of this. So this is per mole of this, which is okay, it's multiplied by 1 because I'm reacting 1 mole. Kilojoule per mole, enthalpy change is in kilojoule per mole. So kilojoule per mole of reacting NaHCO3. Here in my equation, I have 2 mole. So it's 2 times whatever kilojoule per mole because I'm reacting 2 mole. Hess law says enthalpy change of a reaction does not depend on which path you take. I can go direct route or I can go indirect route. So coming down, delta H1 times 1, going against this, so it's minus 2 times delta H2. The actual practical is pretty similar. You weigh the mass of the solid, but you don't use this in MC delta T because this is solid. Your solution your solutions will result in this temperature change. This is endothermic, it's the opposite of exothermic, starting, and then the temperature is going to drop, and then you extrapolate the other way. Extrapolate, extend it. This is the time when you added in the solid. So this is your final, not your initial, because you started from here, you end up here. TF minus TI is negative. So your heat energy is going to be negative. But then when you do this kind of thing, so you can get blah, blah, blah. MC delta T, this student made a mistake because this is the mass of the solution, not the mass of the solid. Okay, this was actually one of the top students. So, you know, it's not just a matter of doing the practical. You need to really think about what is actually happening. Okay, so it's the mass of the solution, not the mass of the solid. Convert your joule to kilojoule. Make sure you have sign. This is endothermic. That's why it's positive, because the temperature drops, right? Temperature of solution drop because the reaction absorbs heat energy. Kilojoule per mole. Enthalpy change is always in kilojoule per mole. So that means you have to convert the heat energy to kilojoule by dividing by 1,000, which is times 10 to the minus 3. On your calculator, this would mean EXP minus 3. EXP should be the button next to the answer button or next to the pi button, something on your calculator. You're supposed to work out for 1 mole of FB1. Do the same thing for FB2. This is kilojoule per mole of FB2. Remember what I said earlier at the beginning? This is for 1 mole of this substance. So if number 2, that was the first one. So you need to multiply by 2 because you have 2 mole of the solid. You have 1 mole of this solid. So Hess law, 1 times that minus 2 times that. You will get assigned a value in a unit. Calculator will not tell you when it's positive. They would only tell you when it's negative. But when it's positive, make sure you also have sign, value, and unit. I think that's pretty much all the time I have for today. You can always review back. I think I made these videos public on my channel, so you can review back all these 6 practicals in detail if you want to. Something I need to remind you of is in the March paper. Yeah, better go a little bit faster. So this was the recently released March 2022. I have released the paper 1 for the March 2022 on the Google Classroom materials. So feel free to go through them at your own convenience for 1 hour and 15 minutes for your paper 1 as well. But this is a confidential instruction, not for the upcoming exam. Please make sure you understand me. This is for the March 2022. And I just want to bring your attention to this thing here. So this is given to the supervisor, yeah? So you might have to twist your head a little bit, but this one is sodium thiosulfate, Fe7. Okay, this is for the February-March 2022. It was just recently released yesterday, yeah? Sodium thiosulfate, it's in qualitative analysis. Why in the world do they ask you sodium thiosulfate in qualitative analysis? This is given. This is one of the sample paper 3. It will be the similar kind of data provided for your paper 3. It's the same thing that Akila would have in her practical exam last week. This was published in 2019 in Reflections in preparing for the 2022 syllabus. You have a periodic table, as I mentioned, in your new paper 3. You have this particular constant. I mean, who knows what they want to ask you based on this constant. These are all the tests I mentioned last week. This is a new test, and this is a new test. So that particular March paper 3 actually asks you to test for thiosulfate. It gives you a precipitate with H+, and it's kind of reminiscent, it's kind of similar to that disappearing cross rate of reactions practical. I think the rest of them are pretty much the same. I've just noted that there are some couple of changes here. Even though this is the key reaction, but be aware of thiosulfate iodine. You know about this in the redox titrations. So what they could ask you to do in a test tube reaction is add a little bit of this colorless reagent to iodine. Hey, why do they ask you iodine? Oh, there you go, iodine. I'm just saying, you know, they are in the new syllabus, so they could possibly ask you on things like this. So be very careful about iodine and iodide. Iodide is colorless solution. Iodine is brown solution. I2 aqueous is brown, but you can add starch. If you add starch, it will go blue-black. Without starch, it will be brown solution. So just be very careful. I think that is all the time we have for today. So I'm just going to, hang on, just don't leave yet. Okay, I'm just going to screenshot the attendance, and I think that's all the time we have for today. Okay, anytime you got a question, just feel free to comment on the Google Classroom, and I'll be more than happy to help you there. Okay, I will share the recorded session a little bit, and hopefully you find the rest of the materials on the Google Classroom useful. Do try the paper one as well from the March 2022 if you find some time. And good luck for your practical next week, and just don't mess up really. Just enjoy the experience and follow the instructions. Okay. All right. Thank you, everyone. Have a good day.
Thank you.
Okay. Bye-bye. Bye-bye.